So, good morning, everybody. And this is the final day of our course. And today we are going to have last lecture, last practical work, and final task for the course project. And then you will be able to send all your works up to 28th January of next year. So basically that is the deadline for all your works, including practical exercises, course project, and exam tasks, which are not yet ready, but I will upload them after New Year celebration. Yes, so basically up until New Year, all you can do now is finish your course project, finish your practical exercises. You are welcome to send them anytime to me. Now I have finally yesterday concluded my project, turned in all reports, so I'm completely free now. And I will be glad to check your works as soon as you finish them. So you are welcome to send them. Yes, so basically this is the deadline. And even if you see that you cannot finish everything in time, you are still welcome to do it at your rate, because even after this deadline, you are still able to get a grade by requesting some special permission in the study department of our university. They will issue that permission and you can accordingly pass the exam. So few of the students last year actually did it this way, a little bit like 1 week or a little bit more later than this deadline, and everything was fine. So it's like not like you it's understandable that the situation can be different, this COVID situation and anything like that. Also, you have many courses, not just this one course, yes, which is all understandable. So at any rate, you are welcome to write me your concerns, and I will try to help you as well with that. So, as for exam, as I have said, the exam will be uploaded at the beginning of the January, right after the New Year. Yes, so you will have 4 weeks, around 4 weeks, to actually finish all course tasks in the exam. So exam will have 2 tasks. One of these tasks will be related to error correction codes. So, for example, if in course project you have had Hamming cyclic code, then in exam you will have some task for Hamming group code, and vice versa. So this way you will actually show knowledge of both codes. And another of the tasks will be on some different topic of what we have discussed over the semester. And there will also be some question you need to answer. So that will be all the exam tasks that you will have to, well, not really have to. Again, in order to actually conclude this course, you need to have, I believe, 4, yes. So each practical exercise, well, actually, as a matter of fact, I think we can open last year's exam. Also, this way you will see how this exam will look like. And there is also a description from last year. Sorry, it's on another screen. So, English here. And here is exam tasks and description. So it will look like this, like you will have, sorry, I think your question. I think there is only 2 tasks. 3 tasks was for our local students. Yes, for you it will be just 2 tasks, just 1 question and 1 task about the code. Accordingly, those who had group code will have a question about cyclic code. Those who had a cyclic code will have to do some work for group code, but it's not really relevant. Yes. So this will be formed as a table, and accordingly you will know what is number of your first question and what is number of your second question, what you will need to actually do. So practical exercises give you each 0.5 points. So if you pass all 6 practical exercises, you get 3. And then you need to do some of the course project. Again, even if you cannot do everything in course project, you are welcome to send what you have. Yes, and it still may be enough to actually pass the course, even if you did some very little, for example, only Huffman coding. I think it is still Huffman coding and some calculations for entropy and stuff like that. It's still enough to actually pass all the course if you have these practical exercises too. But if you do everything, you can get up to 4 points for this course project. So that will give in total 7, and exam also gets you 1 point per each. Yeah, so that gives you up to 9. So deadline this year is 28 January of the next year. Yes, and accordingly you send all your tasks, all your answers by email, just like any practical exercise or course project. So this will be our grading procedure. Yes. So then let us go to the lecture. Today we are going to discuss non-binary modulation types, something we use in Wi-Fi networks, in LTE technology, and 5G will also definitely use such type of modulation. Basically, what actual modulation type we are using in our daily communications, telecommunication systems, I mean, and basically how do they work and what is the difference between those simpler methods like binary amplitude shift keying, binary phase shift keying, and so forth. And why do we need to do that? Yes. What was wrong with these modulation types, which we discussed previously. Then you will have also practical exercise about this topic that Mr. Chen will show you and explain. And after that, on our third pair, we will discuss again. Mr. Chen will show you the final task for course project, adding the coding and checking how noise immunity improved because of this coding. So last week you had made a simulation model that shows you bit error rate depending on signal to noise ratio. Yes, so basically here we have SNR, here we have BER, bit error rate or error probability, PR, yes, and you have obtained how this looks for your specified modulation type. What today we are going to do in the course project part is to actually find another one with coding. So you had some group code or cyclic code in your course project, so you are going to add this coding into simulation and see how it improves. Yes, so basically we will have some coding gain. So for example, if this is 10 at the degree of -6 error probability, and before coding it required a signal to noise ratio, for example 15 decibel, after coding it will work with lower signal to noise ratio, so meaning that noise will be stronger, but nonetheless the error probability will be still the same. So that will be your final task for the course project, and also something similar will be in practical exercise as well today for non-binary modulation. But okay, I digressed a little bit. So let us start our lecture then. And yes, we start by remembering what we have previously discussed. We have previously discussed different modulation types. So here we have amplitude changing depending on what symbol is 0 or 1. Accordingly, we had amplitude of 0 and amplitude of 1. Here we have frequency changes. And here we have phase changes, yes. And each of these signals, S1 and S2, contains only one bit, so either 1 or 0. So what we can do further is to combine multiple modulation types and get more different signals. For example, signal S1, signal S2, signal S3, signal S4, and so forth. Each of them has exactly the same time interval as before, as here. So, for example, let us assume that this is, for example, 10 microseconds. So here we also had 10 microseconds. However, this time we can send actually more than one bit in these time durations. So for example, here we can send 0, 0, here we can send 0, 1, here we can send 1, 1, and here we can send 1, 0. I will explain this odd order a little bit later, but I did that intentionally. So it's still 10 microseconds, but now we send 2 binary symbols instead of 1. So it's obvious now that this non-binary modulation actually allows us sending data faster. So as you know, today we all want as fast data transmission rates as possible, and these non-binary modulation types are what exactly is allowing us to do so. So this is actually very similar to this non-binary line code we were discussing in a few months ago, I believe, yes, where we had 4 different voltage levels. So for example, here we have plus 5 volts, here we have minus 5 volts, here we have, for example, 1.3 volts, and here we'll have, for example, minus 1.3 volts, yes. So each voltage level send 2 binary symbols, and this in total gives 2 binary into 1 quaternary symbol. So these are quaternary symbols, Q symbols, because it can accept 4 different values, and these are binary symbols because they can accept only 2 values. So we combine 2 binary symbols into 1 quaternary symbol and send it as of such. So similar approach will be used for this non-binary modulation. But before that, we can actually discuss benefits of using this approach. So as I have already said, our purpose is to increase the data transmission rate. And there are 2 ways how we can actually achieve that. So considering that most of the systems we are using today are working with multiple users, so we have multi-user systems. So we can increase the capacity of the entire system, and not necessarily a single user will benefit from that, because, well, we may just as well add more users instead of giving more data rate to a single user. So there are 2 ways how to achieve that. First of all, we consider that we keep the symbol duration the same, so tau binary, and actually it's not tau, it's in this T capital, yes. So this is binary symbol duration, and this is non-binary symbol duration. So wait a minute, this is actually wrong. So here we have not 2 but exact equation. Yes, we keep it the same symbol duration and binary duration, but the frequency bandwidth did not change. Also, yes, because we didn't use any shorter pulses, and therefore, accordingly, we transmit all the same data. So here we had data 0, 1, 1, 0, 1, 1, 1, 1. So basically, we transmit all this data twice as fast. So it's pretty obvious how this improves the data transmission rate, because now in this duration we send not just 1 bit, but 2 information symbols. Yes. So accordingly, we finish this transmission faster. Here we couldn't send this one because we need to know 1 more symbol in order to decide what of these 4 levels we will have. Yes, so accordingly, when next symbol will be available, we'll send 1 more as a batch of these 2 symbols. So data transmission rate, therefore, improved twice. Yes, so we have now twice as fast transmission, the same bandwidth. So bandwidth did not really change. Yes, and accordingly, well, everything is nice. Yes, so far. Of course, there will be some drawback. We will discuss that at the end of this lecture. But nonetheless, we can deal with them and basically benefit from this increase of data transmission rate. So this is the first case when we actually keep the same duration of the symbol. So if the duration is unchanged, the bandwidth doesn't change either, yes, and the data transmission rate is increased accordingly. So imagine here now that we will have not 2 by into 1 Q, but something like 8 bits into one, I don't know, octal, yes, symbol. So octal. So basically this will mean that we will have 256 voltage levels, and each of these 256, which is 2 at the power of 8, yes, which is this 8, will accordingly have 8 bits code word assigned to it, and therefore and if we keep the same symbol duration, yes, we will be able to increase our data rate 8 times. So basically, just as much code word symbols we have, this is actual increase in the data rate. So here we had 2 symbols in the code rate, so we get double increase. If we will have 8 code word symbols, we will have 8 times greater data rate. So this in general can be described as M, yes, increase. Another alternative approach is to actually keep the duration of binary symbol the same. So here, as you see, over this time interval of 2 binary symbols, we have sent 0 and we have sent 1. And the same thing happens here. One symbol transmits 2 of these bits, so we can afford to make it twice as long. Yes. So over this time duration, we still send the same symbol. So we didn't really increase data transmission rate. So our data transmission rate remains the same, as it takes exactly the same time to transmit the same information. However, our bandwidth now is twice as small. Yes, so we benefit by reducing the bandwidth required for these signals. Naturally, these rectangular pulses change much slower than these. So from signal theory, you should remember that if we have, for example, this type of the rectangular shape pulses signal, it will have one spectrum, which is accordingly something like this, yes. However, if we'll use even shorter pulses like these, for example, then it will have spectrum which is wider. So basically here we have this, there we have this, here we'll have this, and so forth. Yes, so the bandwidth is this range of frequencies where we have our spectral components of the signal, and this bandwidth increases accordingly with the duration of the pulse, and to be more exactly, proportionally. So if you make twice as short pulses, then your bandwidth will also be twice as small. Yes, no, twice as longer pulses. Then the bandwidth will accordingly become shorter. And if you make shorter pulses, then the bandwidth will increase. So that is actually the reason why we cannot increase our data rate infinitely, because it is proportional to bandwidth. So if you want to increase the data rate, you have to accordingly increase bandwidth. And this bandwidth is limited resource. We have to split between users. So one user gets one part of the bandwidth, another user gets another part of the bandwidth, another user gets a third part of the bandwidth, and so forth. So in multi-user systems, we have to distribute this bandwidth between all the users. So if one user will request twice as smaller bandwidth, that will mean that effectively we can actually now, instead of 4 users, have 8 users. And each of these 8 users will have the same data rate as before. So effectively, for the entire system, we have increased data rate twice. Yes, so this is not for a single user, so not one user gets this data rate, but all the system. But user also doesn't lose his data rate. We just can afford to add more users to system. So this is accordingly the same for any other case when we have more than 2 bits per symbol, m bits per symbol. Yes, so this is bits per symbol. And accordingly, the more bits we can put into a single symbol, the greater is our benefit, but also it will come at some cost. So, as I said, we can have two options. First of all, we can increase a number of channels. Yes, number of channels, and each channel maintains its original data rate, or we can increase data rate of single channel. Yes, so we even have a choice how would we like to distribute this increased data rate. However, the main disadvantage is that we now have smaller distance between the signals. So if you remember, during the lecture, we discussed the distance between signals for binary amplitude shift keying, for binary phase shift keying, and for binary frequency shift keying and for binary phase shift keying. Yes, and the greater this distance was, the smaller was the probability of the error. So more noise is needed to convert one signal into another. Naturally, if we now have more signals, the distance between them will also be smaller, and as of such, the errors will become more often. And accordingly, that is our disadvantage, that we increase the error probability. However, you know that we have codes that can correct errors, so we may just as well add stronger code to address these issues, and everything should be fine. And you will see that in last task of the practical for course project today by your own eyes, when you will get that improvement of the noise of the error probability because you added code. Now we added a very simple code, Hamming code, which can correct only one error. Of course, we can use stronger codes, yes, instead, and get even greater benefit from that. So let us start discussing actually non-binary modulation types in radio frequency. So the first idea is to use phase shift keying because it was actually originally the strongest against the noise. Yes, so basically what we want to do is actually use as a base the strongest modulation type and try and improve it to allow us send more signals at the same time. So we discussed binary phase shift keying. Now we are going to discuss quadrature shift keying. So that means that now we have not two signals, but four signals. And each of these four signals will have different phase shifts. Yes, so basically signal 1 has 0 phase shift, yes, and it accordingly can be just erased. Signal 2 has phase shift of p divided by 2. Signal 3 has phase shift of p. Signal 4 has phase shift of 3p divided by 2. And each of these signals accordingly carries two binary symbols, yes. So this way is exactly what we've been talking about, that we put more information into a single signal. Now, by using school trigonometrical formulas, we can convert these expressions. Yes, so basically, if we add 0 here, nothing changes, and we are left with this sine wave. If we add p divided by 2, we get cosine instead of sine. Then if we add p, then we change the sign of the sine, and if we add 3p divided by 2, then we get both cosine and change the sign, because this can be actually expressed like p plus p divided by 2. So that means we do both of these things to this signal. So also, I'd like to remind you that these signals are actually orthogonal. Yes, because cosine and sine functions of the same frequency are orthogonal. Yes. So if we draw these signals as a vector diagrams, then we'll get one signal. So, for example, this will be sine signal. Another signal, this will be cosine signal. Third signal, this will be minus sine signal, and accordingly minus cosine. So for noise immunity of the system, what matters the most is the shortest distance between two signals. So it's either here, or here, or here. Of course, we also have this distance as well. Yes, but naturally, we need to consider the worst case scenario when the signals have this short distance. So basically, as a result, we consider that minimum distance between signals, just like the minimum distance between code words for correction codes was defined as Hamming distance, yes, and it affected the number of errors the code could correct. Exactly the same, this will be the main factor deciding the noise immunity of the system. And it turns out that it's not just still not as bad, yes, because actually this is exactly the same as for frequency shift keying, binary frequency shift keying. So we lose some noise immunity. It's no longer just as good as for phase shift keying, but it's still good. And furthermore, we now send not one signal, binary signal, but two binary signals. And this is how it works, yes. And as of such, this orthogonal structure of signals will be even more useful to us when we'll design receiver and transmitter, because, well, now we need to actually see the means how to send these signals, how to generate it, and how to receive it. So also, of course, we could use phase shift keying with 8, for example, 8 PSK. Then in that case, we'll need to divide 2p, all the circle range, yes, into 8 equally spaced points, yes. So that will give us 1, 2, 3, 4, which is QPSK, and then accordingly 4 more points. Yes, so this will be our constellation of the signals, and each of the signals are different by the angle of p divided by 4. So we go p divided by 4 and get next signal, p divided by 4, next signal, and accordingly 16 PSK and so forth. But usually the highest amount of these points is 8 PSK, while we still get good enough noise immunity. For example, 16 PSK is not as good because we can have something better. And we'll discuss it shortly. What exactly will be that? Naturally, the smaller is this angle, the easier it is to confuse one signal for another, and the higher will be the probability of the error. So for that reason, we do not really intend to use more than 8. And we also usually intend to use power of 2. Yes, so that would give us either 2 or 4 or 8 or 16 or 32. Because as you know from information theory, in that case, entropy will be maximum. Yes, so that is the reason why we choose this power of 2 as the number of signals, usually. Yes. So, however, in practical considerations, so I have drawn this constellation like this to you, yes, in previous slide. So we had this QPSK constellation. In practice, however, we want to slightly change it a little bit by rotating everything by the degree of p divided by 4. So that now our 0, 0 is not here, but here. Our 1, 0 is here. Now gets to here. 1, 1 gets here, and 0, 1 gets here. This is because in this way it's more convenient to make receiver and transmitter. Yes, transmitter and receiver. So you will see now for yourself how this improves, how this makes it easier for us to actually make this signal, to generate it. Yes. and to receive it as well. So this is the idea. And then now I have said previously that this is intentional order of assigning these symbols. Yes, because naturally order would be 0, 0, 0, 1, 1, 0, and 1, 1. Yes, here we have even differently 0, 0, 1, 0, 1, 1, 0, 1. This is made intentionally as this distance is smaller between this signal than any other. We really would like to have here minimum number of errors. So consider, for example, that now instead of this assignment, we are going to make this natural ordered assignment. So basically, let us draw another picture here for comparison. And accordingly, we make the same constellation. Now we assign them in natural order. So 0, 0, 0, 1, 1, 1, and 1, 0. No, so sorry, again, I assigned them into so-called gray coding. Yes, so natural order would be, so this is 0, this was 1, this is 2, and this will be like 3. Yes, so this is natural order. So what's wrong with this natural order? The problem is here. So if because of the error we misinterpret this signal as this signal, so instead of receiving signal 0, we have received signal 3, in binary form, this will produce two errors. So we sent 0, 0, we got 1, 1. So that accordingly gives us two errors, and it's not really good. Much better if we, in the same scenario, send 0, 0 and receive 0, 1, where we have only one binary error. And our, for example, if we use Hamming code, yes, in this situation, Hamming code will be unable to help us. In this situation, Hamming code, considering that all the other symbols are correct, will be able to help us. Yes, and in fact, gray coding ensures that we have this minimum difference between each of these pairs. Yes, so that is called gray coding or gray mapping. Yes, so this and this differ only in one symbol, these two only in one symbol, these two only in one symbol, and these also only in one symbol. Of course, here we have difference in two symbols, but you can see also that the distance is twice as no, not really twice, but square root of 2 as great. So here noise needs to be stronger for this error to happen. And of course, probabilistically speaking, the probability of such event is lower. Yes, and therefore it really doesn't worry us that much as protecting these symbols, which will be the most cases of the error. Yes, in most cases, error will be happening because of this transition, and this transition will happen not so often compared to this transition, because if noise is so strong that this happens often, this transition will happen even more often. So regardless, number of such transitions will be much smaller compared to these transitions. Yes, and accordingly, that's why we want to protect these most probable cases. Yes, by putting them in gray coding. Accordingly, if we use, for example, 8 PSK, we can design gray coding as well for that case too. So let's try and write it down. For example, 0, 0, 0, then 0, 0, 1, 0, 1, 1. Then we can have, for example, 0, 1, 0. Then we need to have 1, 1, 0. Then 1, 0, 0, 1, 0, 1, and all 1. No, 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 no. It's not good, because here we now have three different symbols. Yes, so let me actually start from the end here and see if I can converge. Yes, I can get it like this. So this will be gray coding, yes? All these distances are protected by ensuring that only one binary symbol is different. And similarly, we can make gray coding for 16, 32, and even more if we need to. So in Wikipedia here you can see more details about that. But now, why exactly we want this rotation? What was wrong with assigning the signals to these points? Well, actually, mathematically speaking, it's more beneficial for us to have this rotation because this way we can express each of these signals as a sum or difference of sine and cosine. Yes, so for example, this is signal 1, which was accordingly here. Yes, so 0, 0. This is signal 1 with this p divided by 4 angle. Next signal will be with 3p divided by 4 and so forth. So what we are going to use here is the formula, yes, of basically a plus b. Yes, that is what is interesting for us here. And it turns out if we open up this in Wikipedia, so trigonometrical identities, and find these formulas. So we need sum and the difference. Which is, where is it? Sine, cosine. So here we have multiplication. It's vice versa, yes? No, but no, this is not exactly the formula I was looking for. I think we don't have these formulas in this slide. Okay, let's see next. Perhaps here. No. Next, here, yes, these are the formulas I wanted to see, yes. And accordingly, this results into sine A and cosine A. Yes, so let us return to this. Because, well, if we write it down completely like this, so this will actually give us sine A, which is omega 0 t, multiplied with cosine b, which is p divided by 4, which we can calculate. We know this value, yes. Then we had plus, I believe, yes. Let's double check it. Oh, this can be closed. So we have plus, vice versa, cosine and sine. Plus cosine omega 0 t multiplied by sine p divided by 4. Then here we'll have same but argument 3p divided by 4. Here we'll have 5p divided by 4. Here we'll have 7p divided by 4. And all of these produce the same sine or cosine absolute values, which are square root of 2 divided by 2 or 1 divided by square root of 2. With only difference that we can get, sometimes we get plus, sometimes we get minus. Exactly the same as here. Yes. Sometimes plus, sometimes minus. So where we get plus and minus, we can actually evaluate here. So sine is an ordinate. Yes. So here we have it as plus for first and for the last. So our sine wave will be plus here, and accordingly minus. Oh, sorry. Plus here and plus last one. And here we'll have it as a minus. Cosine, however, is positive for the first and for the second. So here we have it as plus, and here we'll have them as minuses. Yes, and it's always gonna be this value, which can be accordingly factored out. Yes, it's here. Yes, and all that is left is this plus or minus, which depends on what exactly is this phase shift. Yes. Furthermore, which depends exactly if we have 1 or 0. Yes, so for example, 1 will be minus and 0 will be plus. So, considering that each of these two signals has, for example, 0, 0, 0, 1, 1, 1, and 1, 0, we can put first digit into first sign and second digit into the second sign. For example, like this, 0 and 0. Yes, accordingly, this way we can actually generate the same signal, sine and cosine, and accordingly calculate it as a phase shift keying. So basically, this is binary phase shift keying 1. This is binary phase shift keying 2. Only this shift keying is with sine carrier wave. This phase shift keying is with cosine carrier wave. And accordingly, we already know how to make transmitter for phase shift keying, how to make receiver for phase shift keying. We only need to put two of them into same diagram and have this factor applied as well in order to get correct values of the signal. So, furthermore, we can describe this signal in complex form. Yes. So, for example, this will be our first digit, and this will be our second digit. Yes. So each of them can get either +1 or -1. And accordingly, you will see for yourself that we no longer need to put here that omega cosine. And in fact, we can get rid of this altogether and simulate just the signal di plus j di +1, I believe, should be here. Yes, probably better to write like this. Otherwise, you may think that it's exactly the same signal. So this is the first, this is the second. If this is the third, then this is the fifth, and so forth. Yes, and I can be 0, 2, 4, 6, and so forth. So this will give 0, 1, 2, 3, and so forth. Yes, so here we definitely have I+1. And without even sine and cosine, we can use this signal to evaluate noise immunity. You will do exactly that thing today, and you will see for yourself that no longer we need to actually generate this very precisely like in your course project, because this spends computational resources, this makes simulation longer, this may result in out-of-memory issues and much of that. And this is much more convenient and mathematically justified. So, yes, this is definitely convenient model. Besides that fact that we can actually consider that here we have one phase shift keying, here we have another phase shift keying. So now we can make the transmitter, which is modulator. And as I said, it consists of two binary phase shift keying modulators, which was amplitude impulse modulation. So basically this converts 0 into +1 and 1 into -1. So in our particular case, this is simply NRZ, yes, conversion into NRZ form, which is a particular case of amplitude impulse modulation. Then we multiply this +1 -1 signal with cosine signal. And here we do the same for the other symbols and multiply it with sine signal. Yes. So basically we need some part of some kind of the switch in order to commutate the signals and send it either in one channel or in another channel. So basically first symbol, so basically that would be A1 goes into this channel, A2 goes into this channel, A3 again goes into this channel, A4 again will go into this channel. So all odd numbered symbols will go into cosine channel. All even numbered symbols will go into sin channel. However, we need some kind of delay, because once we had this first symbol, here we have nothing. Yes, so we need to wait when we have the second symbol. So it will go here. However, it will be too late for this part. So for that reason, we need to put here this delay to keep this first signal for one interval, so that when second signal arrives, it will be ready here at the output of this delay, and these two amplitude impulse modulations will be calculated at the same time, these multiplications at the same time, and then we'll have them added up together according to this formula. Yes, so basically, according to this formula, here we have cosine with sine, here we have sin with sine, then we add them together and have this multiplier as well. Yes, so for that reason we add a delay here and intentionally delay first signal for one time interval. It will then similarly work with third and fourth and so forth. Yes. One more thing, we need here to have cosine carrier wave and here sin carrier wave. This does not mean that we have to make two generators. We can use single generator and change the phase of this generator by p divided by 2. Yes, so this is called phase shifting. So we have one copy of the signal without phase shifting, and another copy of the signal has phase shifting, and is therefore converted into cosine. So here we have sin signal. Here we'll have sin of omega 0t plus p divided by 2, which is cosine, and accordingly everything works up together. Of course, sampling here and clock synchronization is very important to correctly operate the switch into correct time intervals to send one symbol into one channel and one into another. Yes, so basically that is two binary phase shift keying modulators. Here we can see how it operates. Yes, so basically, if we wouldn't have this delay, for example, consider that we have no delay here, then all these symbols would be earlier here, and we don't have here, here, not here, yes, here and not here, here and not here. And the problem would be that they do not coexist at the same time. Yes, so we intentionally add this delay so that our symbols will be existing at the same time, so we can calculate our sin and cosine signs correctly. And then, accordingly, this produces the waveform of different initial phase. So here we have 0, 0 initial phase, and our signal starts as sin with p divided by 4 initial phase. Here we have 0, 1, and this is actually 0, 1, and this is actually 3p divided, no, 7p divided by 4 initial phase for the scene. Yes, because our scene is basically almost ended, and so forth. So basically each of these signals have its initial phase. What you can see here is these jumps, these phase changes, which can sometimes be very steep. Yes, this is not good. This is basically well, how it's called, interruption point or something like that in mathematics. I don't really remember, honestly. Much better when phase is changing like this, yes, without these losses, yes. However, our data is random and we cannot do really much about it except for some intentional changes of the phase source signal, but this is very complex problem. What is this results in? This actually increases bandwidth. So these jumps increase bandwidth, and therefore it can partially eliminate the benefit of using this modulation type. Yes, because we wanted to use this modulation type in the first place to either increase data speed or reduce bandwidth, yes, which is both, which is actually benefiting us both ways, yes. So because of this particular thing, we really cannot enjoy it to the full extent, and we need to use something called continuous phase QPSK. Yes, so this is the further development of this method, which will ensure that no such jumps are happening. Yes, that signal will always be continuously changing, yes, without these interruptions, so that bandwidth is not increased too much. Now, for the receiver part, as you imagine, this means that we will need two BPSK receivers, one for cosine signal, one for sine channel. Yes, so here we have cosine, here we have sine. Yes, again, we have same carrier recovery generator, yes, which generates sine wave. This sine wave is converted into cosine with this phase shift keying, and it goes directly as sine wave here. Then we have optimal correlation receiver. So we multiply our received data with carrier signal, then we integrate it and read result and compare it with 0 for binary phase shift keying. Yes, exactly the same way as you were doing that in your practical exercise 4. The only difference that now we need to do that 2 times. Yes, we do this for the cosine carrier, and exactly same signal with exactly same procedure goes over here another time, yes, with sine carrier. Now here we get either 1 or 0, and here we get either 1 or 0. But remember that during the transmission part we intentionally delayed the first symbol. Yes, so now we need also at the end intentionally delay the second symbol so that they have the same delay. Yes, because now first symbol is 1 bit later, and we cannot really undo that in any way. Yes, because we cannot go back in past. We only can delay the second signal so that it will match. Yes, so that for that reason we put delay in the receiver second optimal receiver part. Yes, now here we have again that switch, which again is very important to operate correctly, so we need correct clock, yes, signal for that reason, and accordingly the switch connects to the output once into symbols. Yes, so basically we output A1 from here, A2 from here, A3 from here, A4 from here, and so forth, turn by turn. Yes, so that's how it works. And finally, let us discuss how we can increase even more. Obviously, that we can make 8 PSK, we can make 16 PSK in a similar way. Yes, but this will have problems because these schematics will no longer be true. This works only for quadrature approach. Yes, when we have possibility to describe each signal as the sum of sine and cosines. And accordingly, we need another approach. Another approach is pretty simple, honestly. We now here put not plus minus 1, but plus minus u. So therefore, we add amplitude into this factor. Therefore, what we get is called not quadrature phase shift keying, but quadrature amplitude modulation. So we keep this quadrature principle and add into this factor different amplitude values. Therefore, this enables us to get more different signals. So for sine or for QPSK, we had two channels, sine and cosine channel, and amplitude could be either +1 or -1. So in total, this gives us 4 different signals. Now, if we add more gradations here, for example, +1, -1, +3, -3, that will give us in total 16 different signals. Yes, and the difference here is not just as big. Yes, basically we only have 4 different values, so -3, -1, +1, and +3 levels. So this is, for example, the 2B 1Q code which we have already discussed in each channel. Yes, in each channel we use that code, in cosine channel and in sine channel. Alternatively, if we add even more, then we get now. So now we have total number of signals here, +1, -1. In one channel is 6, yes, because we have 3 that are positives and 3 that are negative. So that gives a total 2 power of 6, which is 64 different signals, yes. So this approach allows us to grow this constellation, well, as long as we'd like to, or as we can afford to, because of the noise situation. So M is 2 power of M small, yes. So where M small is the number of bits per symbol, M bits per symbol. So that means for example, QAM-16 modulation type, which we will discuss in the practical exercise shortly, we have M equal to 4, and we send 4 binary symbols with 1 signal at the same time. So that gives us 4 times greater data rate compared to simple binary phase shift keying. Also, of course, it will have much lower noise immunity, but again, as I said, we have means to work with that. So sometimes this data transmission rate is just too important for us, considering that, for example, in Wi-Fi networks, you may be very close to your Wi-Fi router, or you may go away. And in fact, what happens in Wi-Fi router is that it has even binary phase shift keying, it has QPSK, it has QAM-16, QAM-32. Each of them has different coding, so code 1, code 2, and so forth. And depending on how far are you from the access point or router, it automatically chooses the most, the fastest option that produces the minimum number of errors. So it considers not only data rate, but also the number of errors. So basically it sends some template data to evaluate the error rate, and it can know how much errors are happening, or at least have an estimate, and accordingly choose better modulation type and better code. So if you are too far away from your router, it will choose the slowest modulation type, the strongest code, and you will have the slowest data transmission rate. If you are close to Wi-Fi router, it will choose this modulation type, which alone gives you 5 times greater data transmission rate, and maybe the weakest code, which will have least redundancy. Yes, and this way it automatically, adaptively changes in time. So for that reason, let us see as example QAM-16 modulation type, and all the other modulation types like QAM-32, QAM-64 work exactly the same way. Yes, the only difference will be this number of amplitudes. So for QAM-16, we now have ±1 or ±3. For QAM-64, as you know, we also add ±5, we can add ±7, ±9, and so forth. We only use here odd numbers, yes? This is convenient for us because, it's easier to have them equally distanced. Yes, so for example, -1 or +1 and -1 have total distance of 2. Yes, so next we'll have also distance of 2, and so forth. So we are working with this original distance, which was between -1 and +1, and increase it even further. So number of the signals is exactly this power of M, and number of bits per symbol is accordingly 4 binary symbols per one modulated signal, yes? So if we draw this constellation, it will look like a grid, yes? So basically that is why it is called amplitude phase shift keying, because phase defines the angle. It can be this, it can be this, it can be this, or it can be this. And this is actually our original QPSK. Yes. Now we can increase each of the components, so cosine component and sin component, 3 times and get different amplitude and different phase. So you can see that the angle is now different here, and the amplitude is also no longer 1. So here we had 1 amplitude. Similarly here, and here, and here, and here, and so forth, yes? So basically, combining this cosine and sin with different multipliers gives us different points, yes? And accordingly, here we also use gray coding. We want to protect with gray coding each of these points. And it is possible. That is very nice for gray coding, yes? That any pair of these, literally, you cannot find any pair that is not protected by gray coding, has only one different binary symbol. Yes, literally any of these short distance pairs which are equally spaced, and the distance is 2. Yes, and here is the distance is 2. Yes, because here we have -3, here we have -1, here we have +1, here we have +3. Now, this distance, however, is greater, so it's okay to have more than one different symbols. It's also impossible to protect even this as well. Yes, all we could do is to make sure that each pair of these symbols here we also have the same distance. Maybe it is not drawn correctly, or it's visually leaving impression that this distance is greater. No, it's not greater. It's also 2, because here we have -1 and here we have +1. Maybe it's stretched a little bit, yes, but other than that, it should be the same distance. So how did we make this gray code apply to this constellation? At the first sight, it might seem to be a little bit tricky, but honestly, there is not much difficult in that. Because as you can see, some part of this code is in green and some part of this is in this violet color, yes, or how to name it other. Well, something like violet, yes. So, and if we look at the green part, like this, we have gray code, which we already know. For each column, here it's the same here, and it's the same here. Obviously, similarly, it works for the row. Here we also have gray code, like this, and the same gray code here, and the same gray code here. So designing this gray code was actually quite simple and pretty straightforward, as long as you know gray code for the part. Now, if you would need 6 bits gray code, then accordingly you would do exactly the same. You split that in half. One gray code goes horizontally, one gray code goes vertically. Yes, and accordingly that's it. Yes. So here it's here I have described how to do that. Yes, and the idea is pretty simple. Yes. So again, this actually codes. So 0, 0 is -3, 0, 1 is -1, 1, 1 is +1, and no, yes. Wait a minute, 1, 1 is +1. No. So wait a minute, 0, 0. I haven't assigned it correctly. Yes, because here on cosine axis 0, 0 is -3, and then sine axis it's plus 3. So we should have this 0, 0, 0, 0 here as this point, yes? But don't worry, in practical work, you already have this correctly specified, this correct constellation. You will not need to think about that yourself. So the idea is that we basically convert these 2 bits into a number, which we then multiply with cosine or sine wave, yes, in this formula, add them up together, and we get our quadrature amplitude modulated signal. But as I said, what we are going to do in our practical exercise is to use this complex analytical signal form. So basically, what you will be sending will be plus 3 plus 3j, for example, and that will be your signal for which we will apply noise directly. So we will not make the radio signal, we will not make the optimum receiver, and so forth. Basically, what we are going to do is just to add noise to this, and this is very convenient for modulation, for modeling, yes, for simulations. And when you need to decide, for example, what kind of modulation and what kind of coding you would like to use in your equipment in future, yes, of course it will be quite costly to make this equipment just to know that it's not good enough, yes. So for that reason, people firstly run some simulations and get some initial idea how it will work, how often the errors will happen, and so forth. And making these simple models is quite good for us. So about this quadrature amplitude modulation then, where it is used. It's literally used everywhere. As I said, it's Wi-Fi networks, it's LTE, yes, it's going to be 5G as well. Digital cable television uses it, digital satellite television uses it. Then, for example, the next question is how big this number can get, yes? So, for example, as you can see here in the standard for digital cable television, we can have up to quadrature amplitude modulation 256. Yes, and accordingly, we can have different bandwidth as well. This is needed for basically different quality of the picture. So you know that we can have HD, we can have full HD, we can have 4K, maybe even 8K, yes, and all of that will require better and better internet connection, yes, or, well, not literally internet connection, but bandwidth, yes, basically. And accordingly, as you can see here, we can have different, how to say it, factors, yes. Well, basically, the idea is pretty simple. This 4 is twice as much as this 2, yes? So if we compare this and this, it's indeed twice as great. Similarly, if we compare this and this, these compare as 2 and 10. So basically, this is some factor, yes? Twice, 4 times, 6 times greater, 8 times greater, 10 times greater, yes? Which accordingly depends on quality mode. So this is quality 1, this is quality 2, and so forth. So this is the idea, yes, not maybe in details how it's exactly working, but the idea is pretty simple. That and different modulation types, as you can see, can provide different bandwidth. So you can look more details for Wikipedia for this standard, yes, but well, the idea is like this. So for bandwidth of 2 megahertz, yes, so this is in megahertz, we can get this as megabits per second. Yes, so for example, for binary shift keying, binary phase shift keying, if we had delta F 2 megahertz, then our data rate would be roughly the same 2 megahertz. Yes, so going from binary phase shift keying to 16 QAM, in theory, should produce us with the same bandwidth of 2 megahertz, should produce us data rate with log 2 of 16 multiplied. So sorry, here we have not megahertz but megabits per second. So should produce us this data rate, which is 8 megabit per second. As you can see, however, in practice, we cannot really achieve that high. Still, we are quite close. Similarly, it's here for CAM32, where we'll have M equal to 5. Yes. M equal to 6 here. M equal to 7 here. M equal to 8 here. Yes. And as you can see, the greater we take this M, the greater it becomes a difference. Yes. So yes, unfortunately, not all bandwidth can be used effectively, mainly because of this problem, which I was describing you here, of these jumps, because they extend the bandwidth, yes, and because of need of use some of filters, yes. And well, basically, that's why we don't get this theoretical improvement. However, still, we get quite good. So here we have, for example, 6 times with something greater, 6 times 0.4, something like that, yes, instead of 8 times, which is still significant improvement over normal binary phase shift keying, yes, and which is twice as much as for 16 CAM, yes. So here and here we can see this double improvement. So now what is the limiting factor? Why don't we increase this number over and over and over and over? The limiting factor is this distance. Yes, so for QPSK, you can clearly see that this distance is greater than for CAM16. And for CAM64, this distance is also very small. So the problem with errors is that, for example, consider that you were sending this signal. Now, because of the noise, what we receive is something here. Yes, and we need to decide by measuring distance to this point and to this point, which is closer. And naturally, because of the noise, it can happen like this, that our signal got into this point, and now this point is closer to what we have received. So then we will receive it as this symbol, which will be the error, which is incorrect reception, which happened because of too strong noise. And what we can see here, that if this distance is constant, yes, basically here we also have the same distance. Then putting more and more signal points into this constant distance reduces the distance between each point. So that means that less and less noise is needed to mistakenly receive incorrect symbol. So that is limiting factor for us. We cannot really put these signals too close to each other if we know that noise can be great. So this actually depends on distance for which we send our signal. I'm meaning the distance between transmitter and receiver, which we measure in meters. So for that reason, I was explaining that example with Wi-Fi router to you. So if you are far away from the router, then it automatically chooses, for example, this modulation type, because it therefore can afford this range, yes, where because of noise signal can go, yes. And accordingly, if you are nearby to the router, it's okay to use this constellation because you are not far away and noise just cannot be this strong, yes, anymore. The noise will be somewhere around this range, yes, only because you are closer to signal and the signal doesn't lose so much energy during its travel to you, and therefore noise cannot really do much harm to it. But again, this depends greatly on channel, on cable. In optics, we also use these modulation types, and as you know, optics are not subject to electromagnetic noise. Of course, they have different problems, but at least there is no such thing as noise, and we can usually use these types of modulation in optical cables then as well. So here is some comparison for you. Yes, that for example, for 16 QAM, 64 QAM, 256 QAM, 124 QAM, which are called rectangular, because they produce all the points. Yes, so for example, let us again ask Google for a little help. So 64 QAM, for example, images, it will have 8 points in a row and 8 points in the column. Yes, so it's completely square. Yes, rectangle. I'm sorry, they are all rectangular. Yes, but it's square. Now, unlike that, for example, comes 32 is not a square of the sum number, so we don't have some points here. Yes, that happens because you cannot write like 32 is the square of some number. Yes, because 36 is the square of 6. Yes, and therefore these 4 points are missing. So it's not square constellation. Similarly, 128 is also not square constellation. So we can check it too. Yes, it misses some more points. Yes, so here, 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 and here. 4 here, 4 here, 4 here, 4 here. Total 16 points are missing. So, and yes, if we add these 16 points, we would get 144, which is the square of 12. Yes, but 128 in itself is not a square. So for that reason, it's sometimes important to remember that not all constellation can be drawn as a perfect square. Yes, only those for whom this number is a square. So, and here we have some simulation results or some calculations results. I don't really know. I'm just presenting this table taken from this source. You can read more about that if you're interested. But the idea is that what we want to know is what signal to noise ratio we need to have in order to get one error in million bits. So we can transmit million bits and only one error is acceptable for us. So for 16 QAM, the signal to noise ratio will be 10 decibel roughly. So that means the signal to noise ratio is around 10 times. Yes, so signal is 10 times stronger than noise. So for 64 QAM, it's almost 100. Yes, so the signal needs to be 10 times stronger if we go from 16 QAM to 64 QAM in order to provide the same error probability. And for 1024 QAM, it's almost 1000 strong times signal must be stronger than noise. So in comparison, that means that if we compare here and here, we need to increase the power of the signals 100 times, and then over the same distance, we will have the same error probability. However, at the same time, 16 QAM has 4 bits per symbol, but 10 bits per symbol are for this modulation type. And therefore, our data rate increased 2.5 times. So if we can accept, for example, cut the distance 10 times because this attenuation is proportional to the square. So for example, if we reduce the distance from 100 meters to 10 meters, then it will be fine to use for us this modulation type. Yes, for example. So this is just to give you some idea. And how big these numbers in different standards can actually get. So it's known that there is standard for home networking, yes, with using quadrature amplitude shift keying with 4096 modulation symbols. And where the SL2 technology, allowing to send data rates at up to 200 megabits per second over the simple copper twisted pair wire, not exactly optical fiber or some complex cable, just a simple cable, yes. well, made with special technology as a twisted pair, yes, still can achieve this data rate, and for that they use this number of signals. So that would give us quadrature amplitude modulation 32,768 signals, yes, which accordingly gives 15 bits per symbol. And it works. Truth be told, it works only for very short distances, but it's still usable and it's working, yes. So hopefully that explains you now all the way we went from the first lecture to this last lecture, how these communications are working, how different codes are helping, and then I'd like to thank you for attending to my course over this semester. I do hope that you found something interesting during this course, and wish you success in your future studies, in your works, yes, and so forth. So thank you. And then in 15 minutes, yes, well, okay, maybe 18 at 9:55, Mr. Chen will take over with practical exercise, and then he will tell you when the course project will be. So we do that everything today, and you will have possibility to complete all your works by this new year, except for exam. As I said, exam will be after New Year. Good for you. Not because I need to do some more work there, but just, you know, to let you also rest a little bit and rest for myself too, of course. So yes, thank you. And in 15 minutes, then Mr. Chen will take over.